Welcome to this Calculus 2 podcast. In this podcast today, we're going to be looking at logarithmic differentiation. This is another in our review series of videos from Cal 1. I wanted to use this video as an opportunity to also review you of a couple of properties of logs. So let's go ahead and start there. When you're dealing with logarithms, there are a bunch of nice properties that we can use to our benefit when evaluating very complicated looking things. Now, recall that logs have bases, and these formulas, or these rules that I'm going to show you, work for any base log. Typically, we think of log as being log base 10, or natural log as being log base e, and I'll use those interchangeably, but these properties work for any base, not just those two. So we'll start with the multiplication property, and that is if you're taking the log of two things multiplied together, then you can separate them as addition. This is one of the more important properties of the log. Sort of the analogous property here for differentiation, for division is if you have two things divided, then instead of it being addition, it's really just subtraction. And there's a good reason for this. If you think of x divided by y as x times y to the minus 1 and use the power rule property that I'm going to show you here in a second, then it really should make sense that this is a subtraction symbol here. The next property, like I said, is the power rule property, and that is if you have a power inside a log, then we always teach this as the power comes outside the log, and it's just the log of the base of the power. So something like that. The other properties of logs that I want to go over are some differentiation properties, specifically if you're asked to find the derivative of the natural log of x, then you should hopefully remember that that is 1 over x. It's a very important log property. Also, because of chain rule, if I ask you to find the derivative of the composition of the natural log with any other function as its input, then the derivative in this case given to us by our chain rule formula, go back and look at the previous video if you don't remember chain rule, is given to you by the derivative with respect to x of the natural log of f of x, which, remember, the outside function here is natural log. So what you'll in essence be doing is the 1 over x, but x is replaced with f of x. So it'll be 1 over f of x, then times the derivative of the outside function, the inside function, and the inside function here is f of x. So it's f prime of x. Put these two things together and you have this very nice formula that the derivative of the log composed with the function f is just the ratio of the derivative of f with itself. That's actually a very important property, and it's the basis for what we're going to call logarithmic differentiation. We're going to demonstrate this with a quick example here. I think after looking at this example, hopefully this will spark a little bit of your recollections from Cal 1 using this particular ability. So let's look at a fairly complicated example. We're going to have x cubed minus 1 raised to the 4th. Let's multiply this by a root here, 3x minus 1. And that'll be our numerator, and then in the denominator, let's put another polynomial here. Let's say x squared plus 4. Now, anytime you're doing logarithmic differentiation, the first thing that you want to start off doing is using our log properties, these guys right here, to make this thing more doable. I mean, as it is right now, if we were trying to take the derivative of this, that would involve a very nasty quotient rule calculation, and we want to try to avoid that. So let's start off by seeing what we can do. We've got multiplication in the numerator, so if we break the numerator apart, that's going to break apart as addition. So let's go ahead and do that step first. Now, I'm using log properties here, so I have to be taking the log of both sides, and in fact I am. So let's start off there. If I take the log of the right-hand side, then the numerator becomes log of x cubed minus 1 to the 4th. times becomes addition when you apply the logs to them. And then finally, the denominator is in the bottom. The bottom gets subtracted. So this should be minus log x squared plus 4 in this case. Now, as we look at this, we've got to wonder, is there anything more I could do here? And the answer is, in fact, yes. If you're specifically looking at this, then what you should be seeing is the first one here, x cubed minus 1 to the 4th. I can apply my power rule to that. That'll make this 4 times the log of x cubed minus 1. Plus, here, recall that the square root, 3x minus 1, is really 3x minus 1 to the 1/2. So that's another power rule. In this case, if I bring the 1/2 down in front, we have 1/2 log of 3x minus 1. And then finally, there's no power here, so I'll just rewrite it as x squared plus 4 inside. All right. Now we're at a stage where I actually can take some derivatives. If I look back over to my derivative rules and I'm doing the derivative of the log, it's 1 over the inside. So in this case, the derivative of this is 4 over x cubed minus 1. Plus, we've got 1/2 times 1 over 3x minus 1. Minus, now this one we have to be a little bit careful of. The inside function here is x cubed minus 1 on this first piece, so that means I need a 3x squared as the chain rule part of that. Here, the inside piece is 3x minus 1, so I need a 3 as the chain rule part of that. And then finally on this last piece, I've got the log of x squared plus 4. If I take the derivative here, it's 1 over x squared plus 4, but I also have chain rule on this, and the chain rule piece, or the derivative of the inside there, is 2x. If I make these look good, put them all together, that gives me 12x squared over x cubed minus 1, plus we've got a 3/2 in the numerator here. And then finally on this last piece, we've got the 2x in the numerator. All right, at this point it seems like we might be done, but I've only taken a derivative on one side. On the left-hand side is this log of f of x. So these things are equal to, well, what is the derivative of the log of f of x? Now, we've already shown that it's f prime over f. So because of that, you're looking at this f prime over f term. Now, I started out wanting to find the derivative of this. That was my whole goal, was to find the derivative of f. Because of that, I've got it sitting over here on the right-hand side, but I've got this extra f of x term. If I take and multiply that over, then what we have is f prime of x is equal to f of x times this big derivative that we just got through calculating. Well, I already know what f of x is. If you go back and look at the beginning of the problem, f of x is this huge quotient. So if I take my f prime and simply substitute f of x for what it is up here, let me go ahead and do that right quick. Then my answer is simply this f of x piece times what I had originally. Now we're not going to want to simplify this any further. That would be a nightmare, but just remember that this piece is the f of x piece, and this piece is the piece that we got from using log properties. Now, even though the numbers and the functions may change, the steps involved in doing logarithmic differentiation stay the same regardless of the functions involved. So you can pretty much remember these steps as a way for being able to do log differentiation for any function that I give you. Logarithmic differentiation, as you can see, is a way to take something that would be really difficult to do by hand and break it up, hopefully, into pieces that are a little bit easier to work with. Thank you for watching this podcast.